Bond energies and bond length. We can use bond energies to help us estimate heats of reaction. So what do we mean by bond energy? It's the energy needed to break a mole of that particular type of bond in the gas phase. Bond energies are always positive. It requires energy. It's an endothermic process. You have to put energy into the molecule to break it apart. If bond energies were negative, then the bonds would just fall apart on their own, and that doesn't happen. So you have to put energy in to break a bond. That kind of makes sense. And a bond is stronger if it takes more energy to break, right? So you've got a thin branch, and you can just snap it with your hands. You've got a thicker branch that's stronger, and it's going to require more effort. You might have to break it over your knee or use a saw or something, right? Stronger bond requires more energy to break. So we can write a chemical equation for breaking this hydrogen-chlorine bond. So here we have the molecule in the gas state, and we're breaking it into individual atoms, also in the gas state. And when that happens, it requires 431 kilojoules of energy to break the bonds in 1 mole of this. So 1 mole of the hydrogen-chlorine single bonds. Compounds that have stronger bonds tend to be more stable and less reactive because it takes more energy to break them apart. In order for a molecule to react, you have to break some of the existing bonds and form some new ones. If the existing bonds are really strong, then it doesn't react very much. We generally talk about an average bond energy because the bond energy will vary depending on what the compound is. And so these are just estimates, and we use averages. So if we look at a carbon-hydrogen bond, we can see that the amount of energy to break that bond differs depending on what molecule that's in. So here we've got methane. So we've got the carbon-hydrogen bond, and on the carbon are 3 other hydrogens. That's going to require 438 kilojoules. If instead of hydrogens over here, we've got fluorines, it's going to take 446 kilojoules. If you put bromines there, 402. Chlorines, 401. The strength of this carbon-hydrogen bond will be slightly different depending on what's going on in the rest of the molecule. So instead of being nitpicky about all of that, we're just going to use an average. So it's not perfect, but it's easier. So we say the average carbon-hydrogen bond energy is 414 kilojoules. That's an average of lots of different compounds. A double bond is going to require more energy to break than a single bond, and so it has a higher bond energy. Triple bond has a higher bond energy than a double and a single. So you don't memorize bond energies, you look them up in a table. So here's a table from your textbook, and it shows a bunch of different bonds and their bond energy in kilojoules per mole. So this amount of energy in kilojoules to break a mole of those bonds. Avogadro's number of the bonds. If we look here at carbon-carbon bonds, here's a single bond, 347, double bond, 611. It's not quite double, but it's getting there. And then the triple bond, 837. So significantly more energy to break a triple bond. One thing I want to point out here is the asterisk on the carbon-oxygen double bond. So the average bond energy for that is 736, except in CO2. In CO2, it's significantly higher at 799, and we run into CO2 a lot, so that's listed as an exception. So how do we use the bond energies? When you break a bond, it's an endothermic process, a positive energy, because you have to put energy into the molecule. When the bond forms, it's exothermic. Conservation of energy. You can't just create or destroy energy by making and breaking bonds. If it takes a certain amount of energy to break, then when you reform that bond, it's going to release the same amount of energy. So we can estimate the heat of reaction or the enthalpy of reaction by adding up the delta H's for all the bonds that are being broken. That's going to be, those are all positive, and then the delta H's for the bonds that are being made. as bonds form, they release energy. So here's a simple example of methane reacting with chlorine. So in order to react these things, they're going to form chloromethane and hydrogen chloride. We have to break the bond between the two chlorines here. And so that's going to require us to put energy in. We also have to break one of the carbon-hydrogen bonds. And so we have to put energy in to separate the two chlorines and to pull this hydrogen off. And energy is going to be released when a hydrogen and a chlorine form a bond. We get an HCl bond being formed, and a chlorine and the carbon form a bond, and so that releases energy. And overall, this is an exothermic reaction that releases energy. So we've talked about chemical potential energy and energy being stored in molecules. We often say that the energy is stored in the chemical bonds. And that's a helpful idea, but it's kind of not quite right. When you break a chemical bond, it requires energy. So how is energy stored in chemical bonds? It's the forming of chemical bonds that is going to release the energy. So an energy-rich compound, something like methane or octane in gasoline, very energy-rich, you can get a lot of energy out of it by combusting it. Those compounds can undergo reactions in which you have weak bonds being broken, so you have to invest a little bit of energy to break the bonds, but then stronger bonds form, and that releases more energy. So it's a little bit like an investment. You know, if you want to make money, you've got a nest egg perhaps, and you don't want to just sit under the mattress, you're going to make an investment. You have to spend some money to invest it, and then hopefully you'll get a return, you'll get more money back than you put in. That's what happens with an exothermic reaction. You have to put a little bit of energy in, but then you're going to get more back. Okay, potential future fuel is methanol. There's the structure. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. Oh, fun. Okay, first of all, we need our balanced chemical equation. So let's look at this. I'm going to draw the Lewis structure for the methane. No, I'm not. I'll do that later. CH3OH. So combustion, what's the other reactant? Oxygen. You have to have oxygen for things to burn. And what are the products? Carbon dioxide and water. Why? Because that's what it does. So to balance this, we've got one carbon on each side, so that's okay. We've got 4 hydrogens over here, so we'll put a 2 here, so we have 4 hydrogens over here. And then I've got a total of 4 oxygens here and 3 oxygens there. Dang it. The odd-even problem. So you could put a fraction in there, or we could just double things. So let's change this 2 to a 4, and we're going to double this one, and we're going to double this one. I'm not messing with the O2 because that's the one I'm trying to tink with at the end here. So now I have 2 carbons here, 2 carbons. I have 8 hydrogens and 8 hydrogens. And now in the oxygens, I have 2 times 2 is 4, and 4 is 8. So I can put, I can put a 3 here. I've got 2 hydrogens over here. This is where keeping track underneath might be helpful. There's 2 hydrogens, 2 oxygens there. And here I've got 4 oxygens. Okay, I'm going to leave the O off because that looks like 40 and 20. And I've got 4 here. So 4 plus 4 is 8. And so I want 2 plus 6 is 8. So that whole idea is from a previous chapter. But, you know, things just come around and get you again. So you can't just forget how to balance things. So using bond energies, you could look at these like we did in that graphic example and figure out, well, what bonds are being broken, what are being made. In my opinion, that it requires an awful lot of thinking. It's maybe a little bit longer, but more straightforward to say, let's just break all the bonds, and then we will make all the bonds, and we'll just add those up. Because this is a state function. Enthalpy is a state function. It's just where you start and where you end up. It doesn't matter how you got there. So I think of this as taking some little Lego structures, and instead of just selectively, oh, I'll take this off, and I'll move this over here, I'm just going to take them all apart and start over. Okay? It's the same net result. So we need to think about, well, how is this attached? So I'm going to make this into a more Lewis-y structure now, because we have to be able to see what's going on here. So the methanol is going to have all single bonds. The oxygen here is going to have it's O2. It's got double bonds. It's kind of messy. And this one, we got two of these. We got, I'll do it kind of at an angle here. These are my old friends, so I know what their Lewis structures are like, but, you know, it might take you a few minutes of thinking about this to figure it out. That's fine. I need to know, are these double bonds, are these single bonds, how many bonds are there, so that I can add these things up. So I'm going to pretend I'm just taking apart everything. So if I have 2 moles of methanol, what bonds am I taking apart? Well, I have hydrogen-carbon bonds. And I have a carbon-oxygen single bond. And I have a hydrogen-oxygen single bond. Right? So I have 3 carbon-hydrogen bonds in one of those. I have 1 carbon-oxygen and 1 hydrogen-oxygen. Does that make sense? See that? But I'm going to break up 2 of these. So these numbers are going to double. So if I break up 2 moles of methanol, I'm going to have 4 moles, no, 1, 2, 3, 4, 6. 6 moles of that, and 2 of this, and 2 of this. You okay with that? Everybody's falling asleep on me. An oxygen molecule has 1 oxygen-oxygen double bond. I have 3 moles of oxygen, so I have 3 moles of oxygen-oxygen double bonds. Actually, I don't want to put that up there. I forgot where I was going with this. I'm going to put that down here. So I have more numbers to stick in here. So I have 3 moles of that. So those are the things we're breaking. And then over here, we have to look at what are we making. Well, I'm going to make carbon-oxygen double bonds. I have 2 moles of this molecule. Each molecule has 2 of those bonds. So I'm going to make 4 moles of carbon-oxygen double bonds. And when I make water, I make 2 hydrogen-oxygen bonds, but I've got 4 moles of that. So I make 8 moles of the bonds. Everybody okay with that? Now we have to go look up the bond energies. So we have to go back to this table, and I'm going to use the chalkboard because I can't keep all this in my head. So I'm looking up, there's a hydrogen-carbon single bond. That's 414. I know we had a carbon-oxygen single bond. That's 360. I remember a carbon-oxygen double bond. And that was the one, that was, oh, I can't point down there. That is so stupid. Down here. Carbon dioxide, right? So we have to use that exception. That's the 799. What else did we have? We had hydrogen, oxygen. That one is here, 464. Carbon, oxygen. Oh, oxygen, oxygen double bond. We'll have to break some of those too. So let's see, 498. It's easier if you can have the problem and the table in front of you at the same time. I haven't figured that one out yet. Okay, so I wrote all that stuff on the board. So to break a mole of hydrogen-carbon bonds, it's 414 kilojoules per mole. So 414, but I'm breaking 6 moles, so it's 6 times that. Okay, carbon-oxygen bonds, 360 for 1 mole, but I'm breaking 2 moles, so I have to multiply it. Hydrogen-oxygen bonds, 464. I'm breaking 2 moles of those. And the oxygen-oxygen double bond, 498. And I've got 3 moles of those. So what I'm going to do is I'm just going to add all that up. How much energy to just take everything apart? 6 times 414 plus 2 times 360 plus 2 times 464 plus 3 times 498. 5626. Anybody else do the math? Did I do it? Okay, thank you. So that's what we have to invest to pull everything apart. And now let's see what we're going to get back. The carbon-oxygen double bonds, because this is in carbon dioxide, those are 799 per mole, and there's 4 of them, 4 moles. And we're making hydrogen-oxygen bonds, 464, 8 moles of those. So we're going to add this up. 4 times 799 plus 8 times 464 equals 6908 kilojoules. This is a little bit like, I don't know, being at a swap meet or going to a garage sale or something. I'm selling these things, so I'm getting money for this. But I'm buying those things. So I'm buying these, and this is their price, and this many at that price. I'm going to add up how much do I have to pay you, how much are you paying me, and then we're going to look at the net difference. So these are negatives, right? This is being released. So I should have put that in there. Negative, negative, negative. So the overall estimated enthalpy is 526 plus 6908. (5626) minus 6908, 1282. So negative 1282 kilojoules. So delta H for this reaction would be negative 1282 kilojoules as written. Is that what it asks me for? It asks for enthalpy in kilojoules per mole. Kilojoules per mole of methanol. This is the amount released for 2 moles of methanol. right? I wrote this balanced chemical equation. I figured all of this out. This is the enthalpy change for this chemical reaction, 2 moles of methanol. What's the enthalpy for 1 mole of methanol? Half as much, right? Divide by 2. So, negative 1282 kilojoules per 2 moles of methanol. So, divide by 2. Negative 641 kilojoules per mole of methanol. Any questions? Come on, chapter, be over already. Okay, bond lengths. Double bonds are shorter than single bonds. They're also stronger. Triple bonds are shorter than double bonds, and they're stronger. And so we can compare these carbon-carbon bonds. We see that the bond length in a triple bond is shorter, and the bond strength is greater. So, whoops. When these two things are closer together, it's going to be harder to break them apart than when they're further apart. So we see this trend. The bond length increases, the bond strength decreases. This is a general trend, but there are, of course, exceptions. Bond lengths can be looked up in a table. You don't memorize those either.